Righty. Good afternoon, everyone, and welcome to Young Transport Professionals, second in our Downer series on Rollingstock maintenance best practice. And part two of this series, it focuses on automation. Alrighty. So our agenda for today, we'll do a quick welcome. We'll do a bit of information about young transport professionals. We'll introduce our presenters and give a presentation, and then a Q&A, 10 minutes, and then a closing. And first off, young transport professionals and Downer Group would like to acknowledge the traditional owners of the land upon which this event is taking place and pay our respects to the elders past, present, and emerging. All right, about young transport professionals. This is a group founded in Melbourne. We have over 1,000 members representing over 170 different companies and 15 different disciplines. And it's focused on creating a network of young young professionals in the transport sector around Victoria and Australia. We have some industry partners, including the Victorian State Government through the Department of Transport, and the Oricon, Jacobs and Mott McDonald joint venture. Our presenters today are Kaylyn Chandran and Mohammad Adinehvand. Kevin is the Maintenance Strategy Manager for the Rollingstock Services team within Downer Group. He has previously worked in the mining company in Western Australia, looking after their fleet of locomotives and ore cars. Having over 10 years of experience in rolling stock maintenance, Kevin is now managing several projects involved in the optimisation of maintenance strategy on their Sydney passenger trains. Kevin has a bachelor's degree in mechanical engineering and has a master's degree in maintenance and reliability engineering. Mohammad Adinehvand is a PhD student at RMIT University, having received his master's degree from Tehran University from Iran in 2013. His research interests include mobile robot motion and path planning, reinforcement learning, and optimal control. His current project aims to design and deliver a robot to traverse inside train bogies to inspect complex and tight environments which exist there. And we look forward to their presentation today. Alrighty, I'll pass it across to Kevin, who can start on his presentation.
Awesome, no worries. Thank you very much for that, Russell. Good afternoon all. My name is Kevin and I'm here with Mohammed today to present the second session to the maintenance best practices, specifically focusing on how we are exploring new technologies to improve our maintenance strategies. So before we go into the presentation, I would just like to quickly touch on what we do in the Downer business. So Downer is an integrated services company that designs, builds, and manages assets, infrastructure, and facilities. We employ approximately 50,000 people across more than 300 sites, primarily located in Australia and New Zealand. We have operations in many different divisions, including road services, facilities, gas, renewable energy, and of course, rolling stock services, to which we belong to. Now, within Rolling Stock Services division, we have a footprint across multiple states in Australia. Currently, we have several long-term contracts, including the maintenance of the Millennium and Waratah Series 1 and 2 trains in Sydney, maintenance of A and B class trains in Perth, together with Bombardier or Alstom now, and the operation and maintenance of Yarra trams in Melbourne, Gold Coast Light Rail in Queensland, and Newcastle Light Rail in New South Wales as part of the Keolis Downer joint venture. We're also currently working on delivering the high-capacity metro trains in Victoria and have recently won the operation and maintenance of the South Australia trains as part of the Keolis Downer joint venture. So as you can see, we maintain a lot of different rolling stocks. So in order for us to continue to deliver value to our business and ultimately to our customer, we are continuously seeking ways to improve our maintenance regimes through the adoption of new technologies. So I've touched on this particular roadmap before in our previous presentation, but I would just like to quickly reiterate it again to show how the adoption of new technology and utilization of data aligns with our overall strategy. So Downer Rollingstock Services roadmap to maintenance excellence involves the adoption of improved maintenance regimes together with strategic technological advancements. Our maturity plan in the our maturity plan in the maintenance strategy coincide with the overall evolution of maintenance. So beginning from reactive maintenance to predictive maintenance. We have also adopted the process of RCM, reliability-centered maintenance, which involves identifying failure modes and selecting the most appropriate maintenance tasks to address these failure modes. This means that as we mature through these strategies, the maintenance plans developed through RCM will consist of a combination of different strategies, and that's why in this model here, it sort of overlaps over the 4 strategies. Now, along with maturing in maintenance strategy, we have also laid down a roadmap in the technology space. So this roadmap is very important and has an immense impact on where we're at in the maturity stage for maintenance strategy as well. So with the introduction of condition-based maintenance, data is required to enable the necessary analysis to be performed. Now, not just any data, but the data that targets a specific failure needs to be determined. At the same time, to mature in predictive maintenance, we need to employ further advanced algorithms to provide insights to the data and enable confident predictions. That's the reason why we've placed such a high priority in advancing in data analytics. So in this presentation, I'll discuss further as to how we go about with utilizing technology, collecting data from our trains, and how it translates to insightful information that can improve our maintenance capabilities. Now, Mohammad will then provide a summary of the research project we're currently collaborating with RMIT University. So for any assets or trains, there are generally 2 types of data that you can collect. One is the data from the train itself, and then the other is the data of the train, which is usually collected through external condition monitoring equipment. Now, maintenance through the use of data from the train itself usually involves utilizing sensory devices that are on board the train to provide insights to the condition of the system or component. Now, these include subsystem data such as current, voltage, pressure readings from the component itself, and event recorder data, which captures the actions of the crews or your drivers and the associated train information at those specific time periods. At the same time, the train has also CCTV data, which is another form that could potentially be utilized to provide insightful information. Now, whilst data collection is vital, manually analyzing this data is very time-consuming, as you can imagine, and would not really add much value. As such, creating logics, or what we call business rules, to automatically inform us of impending failure is as crucial as the hardware that collects the data itself. It can range from a simple algorithm that triggers alerts when a certain threshold is met, to complex machine learning algorithm that enables prediction. So in the following slides, I'll just provide some examples of use cases that we've developed utilizing our data analytic platform, TrainDNA. So the first use case here is the airbag pressure leak fault report. So basically, the airbag is a component on the bogie that forms part of the secondary suspension. So you can see here on the diagram on the right. And the purpose is to ensure the train is level and appropriate passenger comfort is achieved. This is a rubber component and is subjected to deterioration and impact damage, which could result in leaks. As such, we've developed a simple report with a very simple business rule that would trigger an alert should the pressure of the airbag drops below a certain pressure, in this case 350 kPa. Now, this is considered a very simple business rule with quite a straightforward algorithm. Our next example here incorporates a more complex business rule that aims at predicting when an EAPS failure will occur. So the EAPS, shown on the right side here, is the electrical auxiliary power supply. and its function is to provide electrical power to operate all electrical loads on the train, besides traction. So lighting, HVACs, air compressor, GPOs, these are some examples of components powered by the EAPS. The EAPS has heat fins that provides cooling capability, and quite often these fins are contaminated, resulting in reduced cooling. So as you know, the thermal management is very important to electrical components and plays a big part in ensuring their safe operation. So regular cleaning of these fins is obviously the most appropriate control to this failure mode. However, given the location of the fins and accessibility issues, it is actually quite an onerous task and can take hours to complete properly for the entire train. As such, we've developed a report that aims at prioritizing the trains that requires cleaning the most, and this is based on utilizing a linear regression to predict the ambient temperature at which the EAPS unit will most likely fail. So for example, I've taken a screenshot of the report and shown on the left side here. So based on this particular report, it's indicating that set or train A10 has a 90% chance that the EAPS on car 8 would fail when the ambient temperature reaches 31 degrees Celsius. So how we utilize this information is that the fleet engineers who regularly reviews this report will then check the weather forecast and determine if in the next couple of days whether the temperature will reach or exceed this temperature. And this would then determine whether a clean needs to be planned in or not. This would prevent any unexpected train delay or cancellation when the set is in service, and would deliver value to both the business and customer. Now, we're also in the process of trying to ingest further weather data in the future, so that rather than having the fleet engineers to physically check the forecast, that can be potentially done automatically. But that's an improvement that we're trying to make to the report. So we've gone through some examples of how we utilize the data from the train itself to inform our maintenance decisions. Now I'm going to run through a couple of examples of data collection through the use of condition monitoring equipment, specifically those that are installed on the network and more commonly referred to as wayside equipment. These are equipment that enables the detection of faults whilst the train is running in service. There are several wayside condition monitoring equipment that provides this capability. The two most common that are used widely by many rail operators in the world are the wheel impact load detector and the bearing acoustic monitor. So the wheel impact load detector, or WILD system, measures the vertical wheel forces utilizing a number of rail-mounted strain gauges, as seen on the top image here. Now, as the train travels through these strain gauges, the defects on the wheels can induce a different signal, which can then be translated to a higher than normal force reading through the WILD system. Now, the forces detected by the WILD system can be attributed to different wheel surface defects, such as wheel flats, spalling, shelling, and aileron. These force readings will also provide an indication of the severity of the defect, which will aid in the planning and scheduling of the train for a corrective wheel turn or replacement. By utilizing such system, it provides the ability for us to continuously monitor the condition of wheel treads without the need to stop the train and enable the transition of wheel tread inspection from fixed time to condition-based. Additionally, we will be able to detect defects quicker, preventing potential damage to rail tracks and reducing the amount of wheel machining required to return the wheel back to a serviceable condition. Now, the next equipment here is the BAM, or bearing acoustic monitor. So this is another commonly used wayside equipment that continuously monitors the acoustic signature of wheel axle bearings and identifies the presence of defects. So as the train travels through one of these equipment, through the unique frequency of noise emission and signal processing techniques, it enables fault identification and classification of the bearings. So similar to the WOW system, the BAM system will output different severities of the bearing defects, which will aid in planning and scheduling of corrective action. So ultimately, this will enable the ability for axle bearing inspection to transition from fixed time interval to condition-based. Given bearing is one of the most critical components on the train and has been a contributing factor to many train delays and incidents, including derailments, having a system that provides early warning and detection of problem bearings months in advance will reduce the risk of these incidents significantly. Bearing life extension could also be achieved if we can accurately monitor their condition and optimize the timing of train removal from service through prioritization of defect severity. This will obviously have a positive impact to both the business and the customer we serve. So in the previous slides, I've discussed about some of the existing technology that Downer have adopted in order to improve our overall maintenance regime. Now, Downer have also partnered with different universities to explore other more innovative forms of technology that have industry applications, and one of them is with RMIT University in the research of an inspection robot. So now I'll pass on to Mohammad, who will be discussing about this particular project. Sorry, Mohammad, I think you're still on mute.
Yep. Thank you very much. I'm here to talk about the new technique to collect the data.
Sorry, Mohammad, just to interrupt there, you're presenting the notes page at the moment.
Okay. That's okay.
Yep, that's good.
Okay. Yep. In this presentation, I'm just going to give a quick introduction about the new technique to collect the data in rolling stock industry. In this presentation, I would like to draw your attention to hardware and software requirement to design a new autonomous platform. For a hardware requirement, we will consider the movement type and how we analyze that movement. We also focus on how we can control a robot to follow some path to collect the data during that movement. First of all, I would like to say that I come from an intelligent automation research group from RMIT University. In this group, we mostly focus on robotic platform, and we also focus on machine learning and computer vision to make a system autonomous. Okay, as Kevin mentioned, for in rolling stock industry or almost all industry, we usually inspect the component based on some timetable. For example, in Donor, they do each 45 days. That is that manual inspection is time-consuming and expensive. So we try to switch or move from manual inspection to some autonomous technique and inspect based on the condition of the system. There are some platforms in market. They usually use a stationary system or a mobile platform. But the problem is here, as can be seen from this bottom view of the bogie is very complicated. So if we just use such a technology, we are not able to get access to all sites of the component. So the aim of this project, we try to design a robot which be able to crawl into the bogie and go inside and look at all component. That would be difficult because design need to be very small, less than 30 centimeter by 30 centimeter. It's also need to be able to negotiate any difficulty, surface transition, and too many obstacles. It also need to be move safely. So to design design properly and to meet our requirement, first of all, we need to think about the hardware, which movement, which type of movement, which locomotion is more suitable for design as such a robot. Most of the robot has a continuous movement. For example, use the wheel or track, or some of them has a step-by-step movement, such a leg robot. Or some researcher use a combination of these two type of movement. In our application, as the environment is very tight and unstructured, look at the movement. It is one main challenges. We also have to think about how we can overcome the forced gravity and move in a 3D space. There are some technique, but we, based on some limitation, we decided to use adhesive principle, magnet or mechanical or pneumatic or chemical or electrostatic force to attach to the surface and crawl into the surface. In hardware requirement, it was required to look at the size of the robot, to I mean the dimension of the robot, or we need to consider the weight, and especially the robot need to be able to negotiate any surface difficulties, such as surface transition, irregularity, and also the robot need to be able to overcome unstructured obstacles. Based on my literature review, most of the robot deal in a very simple environment, so it seems need to design a new robot which be able to move in a tight space, but be also quick. After a long story, we designed this tiny robot. It is less than 12. It can reach half a meter. It means it can extend its body to half a meter, but at the same time it can squeeze itself to around 10 centimeters. So that is a great feature for our application. The reason we designed such a robot is that, first of all, I would like to say that for any movement from one place to another place, we need just 6 degrees of freedom to do such task. But the path planning or movement is not just the main task that robot want to do. Robot want to deal with some singularity in design, or robot want to deal with obstacles. So in order to make robot more flexible, we add extra freedom to system to make a system redundant and use that redundancy to path planning. Just consider that most of the industrial robot has 6 degrees of freedom in a huge and big space and size. But here is we use 12 degrees of freedom, 6 extra redundancy, and that is a great feature of the robot. The robot also have a 2 gripper in its head two switchable magnet, which is mechanically can turn on and turn off those magnets, and we can use this switchable magnet to attach to the environment. They can be mechanically switched, and that would be good because it doesn't need to consume too much power to do that. The next key feature of this robot is that in most of the industrial robot, each joint has own limitation. For example, they cannot rotate more than 180 degrees, but this design, its main body has ability to rotate 360 degrees, which can be used to carry any tools or camera to data collection. That's a great feature because the robot is able to attach to the surface and without any disturbance on uncertainty on the system is able to collect the data. The design is very simple. Just move from one point to another point, change the switch, change the magnet, and follow the new path. For example, in here, robot find the first point of contact point, follow the path, and after that change the activated magnet and follow the new path. I would like to say that most of the industrial robot can be categorized in two types. One is open chain robot and another is closed chain robot. Each of them has own advantages and disadvantages. But in here, as can be seen, robot is able to move and switch between these two types of movement. So that's the great ability of the system. In a closed chain, as I said before, it's easily able to collect a large area, look at the large area of the bogie and collect the data. We try to build a robot. We first focused on designing based on 3D printing, but we didn't get a good quality and results, so we decided to machining, and because of the COVID, we tried to complete the robot. We just built one part and we tried to complete it. Hope COVID lets us to do that. After designing a robot, now we need to think about the software and mind of the robot. How a robot can find a path from one place to another place. Traditionally, a user define a location and give the robot that is your path, please follow that path. But that's not useful on a structure and crowded area. Look at this part of the robot. It would be very difficult to find a path by user. So we need to let the robot to think and make a decision and find a path. During that path, robot need also consider the collision. Itself collision, internal or external collision by yourself and collision with the environment. And also we need to design a controller to push the robot follow that path. So these three elements should be considered in the software part of the design. In path planning, before going further, that is a little technical part, but it is required and it is very important to explain. As I said, for example, we want to place the camera in a location, or we want to place this gripper in the next point of gripper. So we design or describe the position of the robot based on some in a Cartesian space. But when we want to move the robot, we discuss or we move the robot in a joint space. So we act on a joint space, we push the joint of the robot to move, but we want to locate a robot in a Cartesian space. So relationship between these Cartesian space and joint space need to be considered and analyzed and find inverse and direct of this relationship. We do that, but why that is important? Because when we want to find a path for robot, for example, in here, robot that is consider that is the initial configuration of the robot, and we want to robot move from this configuration to this given goal. So that configuration can be described as a point in a joint space like this one. And also the goal configuration can be considered as another point in here. And now we want to find a path from here to this point in a safe zone. That black area is a description of the obstacles or internal limitation of the robot. The main technique is used rapidly exploring random tree. Randomly, we select a point in an environment, in a space, and connect them, and finally find the proper path. With this technique is very well known in robotic community, but need to be developed, and I'm thinking to develop it and combine it with some optimal control technique. However, until now, I test my system in some traditional scenario. For example, stair climbing, stair path planning is one of the traditional tested, and if robot able to overcome such environment, can be considered, okay, that robot is able to do extra tasks. Or narrow passage path planning is one of the main challenges in robotic community, and as can be seen here, our design is easily able to overcome such obstacle, not only based on predefined path, but also robot is able to find the path by itself. That is a great ability of the design. And also a step climbing is another challenge for robotic. For example, just imagine a wheel robot or track robot. None of them is able to overcome such obstacles. Finally, we test our system in a real environment. Just consider here, robot stay at the initial configuration, and we want to robot move from this configuration to attach to the wheel. That is too far from the initial configuration. So robot first find the intermediate goal, then find a path to reach that goal, intermediate goal, and change its configuration. And finally, after switching the gripper, find the next point of, for example, in here, it's find this intermediate, and after that, again, find the path to reach the next goal. As can be, just let me to repeat it in here. Moving from this tiny area, it's very difficult and challengeable. But when robot reach here, it's quit its body, and finally be able to find the next point of interest. Yep, thank you. We try to complete it and test it in a real environment, but as I said before COVID, we just prioritize our task to compromise between solve a solution in a simulation or test in a real environment. Thank you very much for your attention.
Thanks, Mohammed. So now we have some time for questions. So I can see one already from Adrian. This is directed towards Kevin. Does Downer have a centrally located data analyst, or do they embed their data analysts in their fleet depots? How do fleet engineers and data analysts work together in order to develop smart algorithms, such as your EAPS example?
Yep, no worries. Yeah, that's a very good question. So at the moment, I would say that our data analyst is located centrally, and we do have a couple of fleet engineers and even design engineers within the depots, which are quite familiar with some of the data analysts or data analytics work, but majority of the design and embed of the algorithm and things like that do happen within our centrally located data scientists and data analysts. Now, that's not to say that we don't work closely with the fleet engineers within the depots. One of the things we've tried and encourage is for the fleet engineers to come up with sort of what we call the business rules, or the algorithm, or even if it's not in a coding environment, more just describing what they want to be able to achieve, and what sort of signals might be available for us to utilize, so that they can then pass that information on to the data scientists within our centrally located team to then explore that further. So that is sort of the structure we've tried to embed within our depots. Yeah, and we find that to be quite effective, because if the business rules and let's just say use case reports are derived from the depots themselves, they're more inclined to, I guess, utilize the information coming out from those reports, and also they will see a lot more value. So yeah, so that's sort of the structure we've embedded.
All right, thanks, Kevin. Yeah, just a reminder to anyone in the event, if you'd like to ask a question, you can use the live event Q&A feature through Teams. So the next one's for Mohammed. So does the user really need to direct the robot to move to a particular location, or could this be pre-programmed to accommodate a particular set of standard bogie designs? And the user just selects what they want to see.
I didn't catch exactly the question. If it's mean we design a specific point for a robot, that's okay. Yeah, we usually define a target for a robot, where robot want to go. But the main problem is that how robot want, for example, robot, let's say, enclose the wheel and want to inspect the brake. And the main question is that how robot can find a path to move from that point, initial position to the goal position. That is the main problem. Just consider a simple robot in a simple environment on the ground, and want to move from 0 to, for example, 10 meter by 10 meter location. That is very easy for robot to understand. Okay, the best path is the linear path. Okay, but if we add one obstacle to the space, that would be not very difficult, but robot want to think about it. If we add 2, or that makes it more difficult. When we have on a structure with lots of obstacle and robot need to move through them, that cannot be predefined. So robot need to think and make a decision about it. I just showed some simulation. In one of them, I just defined a predefined path, but for a very simple movement, I did lots of trial and error to define a simple path. But for define a path in a real environment, that would be that cannot be happened by just user, cannot be defined by user. User just need to define a goal, not a path.
Okay, I think, yeah, this kind of answer kind of relates to the next question from Cameron. Could the robot just have a set of predefined movements or routes to go to a typical inspection location? I think I'll just add to that question.
Yep.
In terms of the path planning, does it require an intense amount of computation to perform, or can it be done on the fly? Do you need to pre-calculate these paths to perform an inspection?
The current technology is that we have a 3D model of the environment, and we use that 3D environment to calculate path offline. That is the existing technology. But we know that the CAD model is different from the real environment. So we try to develop the path planning technique to make it able to find the path online. We call it as a opening window. Just robot use its sensor, look at the environment and a part of environment, not the whole of the environment, and robot know where we want to go. So based on that new open window, robot make a decision to find a path for the next step. And when moved to the intermediate point, again, based on its sensor, another window will be opened. So, I mean, there are some technique we can use it online, but that is a part that I'm working on it, how to make sure that online technique is safe and reliable. But as I said, most of the technique is offline, and use those paths by some adaptive controller. We can push the robot to follow that pre-calculated path.
Thanks, Mohammed. So I have another question from Tom. What proportion of most bogies can be inspected this way? Would the addition of something like a short, movable borescope allow full access to all external parts? I think maybe as a kind of addition to that, have you thought of other sensors and things to add to the robot?
At this stage, we use two type of data because we did it in a simulation. We use two type of data. One is distance data, and another is image data. I'm working on the image data. We currently complete the path planning based on the distance data. For example, we just we decided to ignore our knowledge about the bogie. We try to create a map or create a 3D model of the bogie based on the distance data that mounted on the bogie. So, that have been done. So, but there are a difficulty to use just a distance data. So we try to figure it out how we can use the image data and fuse them with distance data. And use these two type of information to properly define a path.
I think I can probably add a little bit on to that. So at the moment, Mohammed has more been working on the maneuverability of the robot. So from a hardware perspective and a software perspective. Now, in one of his slides, he's shown that you can have a camera that's attached which can rotate 360 degrees. That's just I guess like generic item that we can include as part of the robot. That's not to say we can't have anything else. I guess at the moment, Mohammad is just trying to finalize how the robot is going to move around the bogie in order to perform those inspection tasks. So more from a path planning perspective, and that's like from a hardware and software view. Yeah.
Thank you.
All right. Well, now that we've got you, Kevin, there's a few questions for you. So one from Luke. Have the automated tasks reduced the amount of corrective maintenance or the number of faults found?
That's a very good question. I'll need to think about an example. So one of the I think in general the answer to that would be yes. It has reduced the amount of corrective maintenance. There's a couple of very established technology out there which does accurately detect defects. So for example, the two that I've mentioned where we collect from the BAM equipment and the WOW equipment. So bearing acoustic monitoring specifically is very, very accurate. We've been able to detect a lot of stress initiation point on the bearing itself, even before they get to a catastrophic failure. And that's like months before. So it has been very, very accurate. And these type of failures or stress initiation point wouldn't have been detectable if we had used our traditional method of rolling the bearing to listen for noise and things like that, because they were quite let's just say small, and yeah, wouldn't have been detectable just through the traditional method.
Thanks, Kevin. So I've got another question from Pez. What measures do you have in place to improve the reliability of data collected?
Yep. So one of the things we constantly perform, and this is something that we've embedded within the depots, is that whenever a report triggers a particular alert, obviously the process is that they need to create a work order so that that particular fault can be reviewed and corrective action can come about if necessary. Now, as I've mentioned before, sometimes those alerts are false positive. So what we do then is we collect all this information, so all the alerts are triggered by the report, and then determine the number of I guess alerts which are in fact true, and those that are false positive, and then we feed that back to the data science team so that they can then improve the algorithm or the business rule to which the alerts are generated. So there's we have embedded a bit of a process to ensure that the fleet, the engineers at the depot communicates the results of these alerts to the data science team, and then continuously improve that process. So yeah, I hope that sort of answers your question.
Sure. So I got another question for Kevin, and then we'll go back to Mohammad. So the next question for Kevin was, do you do any analytics on track geometry parameters or vehicle response data?
Good question. So at the moment, majority of our data analytics are done from a rolling stock perspective. However, we do have some equipment that we've actually recently installed on some of our trains, and they're more to do with track condition monitoring. Now that's still quite in infant stage. An example would be we've actually got some bogie or bearing sensors installed literally on the bearing itself, which obviously can detect vibration, temperature, and those particular sensors can actually detect any sort of track defects as well, based on, if there's any defects on the track, it would create a different vibration signal, and then such could potentially be captured by these sensors. So yes, we do have some capability. We haven't really explored this space as much, simply because we're more of a rolling stock maintenance division. But I mean, at the moment, we do have some equipment on our trains that has that ability.
All right, thanks, Kevin. And back to you, Mohammed. There's kind of a couple of questions here that I might kind of roll into one. So how will the robot traverse through a bogie of unfamiliar design? Is mapping of the environment something considered, or is the 3D environment predefined for the robot? That was from Joseph. And questions from Tom was, does the robot have any sensors to detect a potential or actual collision, or any deviation between the CAD and reality may result in fouling, falling off, or getting stuck?
That is a two different approach to look at the system. First of all, we in our group, some people work on the abnormality detection algorithm based on some machine learning. In that abnormality detection, based on some previous data that we give the system, and we train the system, and the system will be familiar to detect the new abnormality of any environment that can be considered as a fault or some or missing the part. So that can be considered as a analyze the data after collecting the data. So that is not the part that I'm working on it. But in terms of movement in a space to collect the data, we have as I said, we have a two simple approach. We have a knowledge about the environment, and we 100% sure that knowledge is true. And based on that knowledge, we define a path. That is not, we can do it in a computer or in a simulation environment, or we can do it for a gaming industry. But in reality, that's not true. So some technical reinforcement learning comes to help a developer to think how we can optimize our path based on data that we observe. So in here, we combine the optimal control, that is to find the optimal path, and plus reinforcement learning to make a decision. Okay, how the robot can be able to make a decision based on the data that can receive from environment. For example, have at this stage we use, as I said, we use the distance sensor. The robot look at the environment, receive the location of the bogie equipment, and based on those information, robot generate a map, a new map for itself, and now we have a map that can be considered as a real, an actual environment, and then we, based on some, as I said, based on our technique, we can find a path. Let me to clarify that this all technique is not a separated technique. So it is not, okay, some people work about the optimal control, some people think about the mapping, some people think about the localization, some people think about the path planning. All localization, where robot is, and mapping, and where is the environment, and how to control the robot, and path can be done as a one strategy and one algorithm. So we call it as a SLAM, simultaneous localization and mapping. We use this technique to combine all algorithm for each step. So that is the way we do that to find the path.
Yep. All right. Thanks, Mohammad. I guess maybe to add on to that, the magnetic grippers, do they have any, say, feedback or touch sensors that recognize once they've, they're in a position to make that firm attachment back to the bogie?
No, we don't have that. We can add a sensor to the gripper. We have a space to do that, but that contact sensor information will be change the definition of the information, and that would be a little challengeable to use such information with distance and camera information and fuse them. At the moment, we just use distance and encoder information. So it means we use the data, and we know where is the, for example, the wall, and we use the encoder sensor to say, okay, what is the configuration of the robot? So based on the configuration of the robot that comes from the encoder information and the wall that comes from the distance sensor, we can say, okay, now robot is able to attach or not. We need to, for example, move this angle a little bit and then reach that point. So if we want to use a force sensor or contact sensor, the story will be totally different.
All right, thanks, Mohammad. Probably I got maybe one question. How is the BogieBot powered current in your current design? Is it all batteries or a tether? And another one, like how scalable is the BogieBot? Can it be made bigger, smaller? I could imagine, you could have a similar thing for big mining equipment or, something really small. So.
The reason we designed such in such configuration, to be honest, is that we can squeeze it to a smaller and make it a little bigger. Mm-hmm. But I used the smallest DC motor available in the market, which able to move the robot. Yep. If the DC motor developer developed better and a smaller robot, a smaller DC motor, we can easily make it design a smaller. In some cases, if we want to make it bigger, I think that's the very easiest part, I think, because we just able to scale it, nothing more. So that is an interesting part. In some design, when we want to make it bigger, we need to consider several things. For example, the torque, the output torque of the DC motor, or I use a special configuration of the gear head, and that would be need to just scale it. And we can use it for another environment as well. We will. That can be I think that design is scalable, so we can use it for.
Alrighty. All right. So it looks like we're approaching the end of our time here. So I'd just like to say to everyone that's on the presentation today that we have recorded these presentations and our previous one from last week, and they will be available through Young Transport Professionals YouTube page. So if you want to come back and review these presentations anytime, you'll be able to do that. I'd just like to say thanks to Mohammad and Kevin for their presentation today, and hope that everyone on the call today has enjoyed their presentations. And thank you very much.
Thank you.
Thanks, everyone.
Thank you very much.
Alrighty, we'll end it there. Thank you very much. Bye.